Welcome back to college algebra. In this video, we'll be taking a look at polynomial and rational functions. Sorry, wrong pen. A polynomial, you probably remember from a previous course, is any function which can be written as p of x equals an x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. So if you can write the function as a string of powers of x, then that function is a polynomial. If there are other things in the function, then chances are it's not a polynomial. So for example, something like f of x is 3x squared minus 9 is a polynomial. Something like g of x equals x to the fourth plus x cubed minus 2x squared minus 5x minus 42 is also a polynomial. Even if it doesn't look like a polynomial at first glance, it might still be a polynomial. For example, h of x is x plus 1, x minus 2, x minus 5. That doesn't look like a polynomial, but the definition doesn't say a polynomial is written in this form. The definition says the function can be written in this form. So if we multiply it out, x plus 1 times x minus 2, that'll be x squared minus 2x plus x minus 2, or x squared minus x minus 2. Then if I multiply that times x minus 5, I'll get x cubed minus 5x squared minus x squared plus 5x minus 2x plus 10, or x cubed minus 6x squared plus 3x plus 10 when the dust settles. Originally, it didn't look like a polynomial, but after simplifying, it does. And so this thing is a polynomial as well. Generally speaking, when we're trying to call something a polynomial, what we're looking for is that it does not contain division, although we do have to be a little bit careful there. If we have f of x equals x over 3, well, x over 3 I can rewrite as 1/3 x. That is a polynomial. But if I had g of x equals 3 over x, here I'm dividing by x. And dividing by x is a problem, so that is not a polynomial. Or if I have radicals, once again, we have to be a little bit careful. F of x is x times the square root of 7. The square root of 7 is just a number. That's not a problem whatsoever. But if I have g of x is 7 times the square root of x, now because it is x underneath that square root, this thing is no longer a polynomial. And finally, our polynomials all involve x being raised to various powers. So if I instead took something and raised it to the power of x, well, that's backwards of what we do in a polynomial. So 2 to the power of x is also not a polynomial. scrolling back up just to grab this definition again. A polynomial is something written as an x to the n plus a n minus 1 x to the n minus 1 plus so on and so on and so on until you get down to a1 times x and then a naught. The leading term in this polynomial, as it's written here, is the one that comes first, an x to the n. More importantly, it's the one that has the highest exponent. And reading off of the leading term, the exponent in question, n, is the degree. And then the coefficient, an, is called simply the lead coefficient. Recognizing the degree and lead coefficient of a polynomial is a very easy step towards understanding the behavior of the graph of a polynomial. So if I have a function like f of x is 3x squared minus 5x plus 7, I can see that this is a polynomial with degree 2 and lead coefficient 3. If I jumble up the order a little bit, give you something like g of x is x squared minus 5x cubed plus x minus, let's make that plus 8x minus 11x to the 5th minus 42. The highest exponent in this expression is this guy right here. So there's my lead term buried in the middle of the polynomial. Nonetheless, the degree of this polynomial is 5, and the lead coefficient is negative 11. One thing that can be a little bit tricky working with polynomials is that for a lot of what we want to do, it is far more convenient when the polynomial is given in factored form. Consider, for example, this polynomial. H of x is 2x minus 5 times x minus 1 times 3x plus 2 times x plus 7. Because this is not expanded out, it's not obvious what the lead term, lead coefficient, and degree of the polynomial actually are. We could simply multiply the whole thing out, and there are instances where that will be useful. But if all we want to know is the degree and the lead coefficient, we can get there by looking term by term or factor by factor. In the first factor, the highest exponent is on 2x. In the second factor, the highest exponent is on x, and then 3x and x. In this case, everything just had x and constant. Sometimes you'll have something that has an x squared in it as well. But to find the lead coefficient and the degree, we can simply multiply together these terms. 2x times x times 3x times x, all told is 6 times x to the 4th. I don't know what the rest of the polynomial is, but this is the lead term of the polynomial. So I can see that this polynomial will have degree 4, and a lead coefficient of 6. Now, degree and lead coefficient are useful for a couple of applications. One of them is an idea known as the end behavior of the graph. If you look at some of the graphs we're familiar with, y equals x, y equals x squared, and y equals x cubed, you see this interesting pattern where going to the right, the function is always heading in a positive direction. Going to the left alternates, negative direction, positive direction, negative direction. In general, that is a pattern that does continue. If you consider a polynomial of degree n, when n is even, you will have mirrored behavior. Right? You don't necessarily have an even function which is perfectly symmetrical, but the end behavior will be mirrored. If it's going upward on the right, it's going upward on the left as well. If n is odd, then you have opposite behavior. If it's going upward on the right, then it's going downward on the left. Follow that up. When we were graphing parabolas, we saw that if we multiplied the x squared by a negative number, it flipped the parabola upside down. So if I squeeze in here one more graph, y equals the negative of x squared, then we have a parabola that's heading downward in both directions. And once again, that's something that will continue. If you have a lead coefficient which is positive, if I can write the word positive, if you have a lead coefficient that is positive, then the graph will go up to the right. If you have a lead coefficient an, which is negative, then the graph will go down. To the right. We call this pattern the end behavior of a graph. And figuring out the end behavior is a giant step in the direction of figuring out what the graph looks like. The other thing we have to figure out are the axis intercepts. So if we can find the end behavior, and we can also find the axis intercepts, then we're going to be in great shape. Right? The y-intercept is always easy. Plug in x equals 0, and all the terms that have x go away, leaving you with a naught. If your polynomial is in factored form, plug in x equals 0, all the x's go away, and you're left with a string of constants to multiply together. Takes a little bit more work, but that's how you calculate a naught. So we can find the y-intercept pretty easily. The x-intercepts are a little bit trickier. To find those, we will use the zero product rule. And that's why it was so convenient to have our graph or have our polynomial given in factored form. Right? If we have f of x equals, say, 2x minus 3, x minus 1, 3x plus 5, and x plus 4. I think that's what we used before. Well, to find the x-intercepts, take this thing, set it equal to 0. And then using the zero product rule, or the zero factor theorem, or however you've seen it named, the product of all of these things can be 0 if and only if at least one of them is itself 0. So we get that 2x minus 3 is equal to 0, or x minus 1 equals 0, or 3x plus 5 equals 0, or x plus 4 equals 0. And solving those, we get x is 3/2, x is 1, x is negative 5/3, x is negative 4. Right? We now know all of the zeros, so that gives us the 4 x-intercepts: 3/2 0, 1 0, negative 5/3 0, and negative 4 0 that we're going to be working with. We can find the y-intercept, as I said earlier, by simply plugging in f of 0. We get negative 3 times negative 1, which is positive 3. 3 times 5 is 15, and 15 times 4 is 60. So this particular curve has a y-intercept 0, 60. Next, we can come up with the end behavior. Let me go ahead and copy this original function, because I'm running out of space on the screen. And again, remember that trick. Take the highest term in each of these. So we'll take 2x times x times 3x times x, which is 6x to the 4th. The lead coefficient is positive. The degree is even. Positive means it's going to go upward to the right. Even means it's going to mirror that and go upward to the left. Fill in the points in question, and we have ourselves the graph of a polynomial. All right, so let's sketch out some coordinate axes here. And I need my x scale to be fairly small so I can figure out where those fractional values are easily. I need my y scale to be very large because I have to get up to 60. All right, and we plot our y-intercept was 0, 60. Our x-intercepts, I'll scroll back up so we can look at them again. 3/2 0, 1 0, negative 5/3 0, and negative 4 0. Negative 4 is right here. Negative 5/3 is somewhere between negative 1 and negative 2. Around about there. 1 and 3/2. Now, end behavior. I know that I'm heading upward over here and I'm heading upward over there. So connecting in then, I cross through that. Then something's going to happen and I'll curve around and get through that. I have to come way up here, make sure I get through that. Go down, curve around here, and a real quick turnaround to get to that point before I head back up that way. My vertical scale might be off a little bit. Those of you who are continuing onward in mathematics, in the study of calculus, one of the big things you look at is how to figure out where those turning points are to make them a little bit more accurate to get a better sense of your graph, but it gives us a good idea of what the curve is supposed to look like just with that. There's one other wrinkle that we have to pay attention to when it comes to graphing a polynomial. And that idea is something called multiplicity. When you study quadratic equations, or you study basic polynomial equations, the idea of multiplicity is presented to you as repeated roots. For example, if I'm looking at the function f of x equals x plus 1 squared, I might write that as x plus 1 times x plus 1. And if I set it equal to 0, I get that x is -1 or x is -1. The fact that the same solution comes up twice is called a repeated root. More generally, multiplicity is a measure of how many times that same root shows up. So we have a solution here of -1 with multiplicity of 2. And it is no coincidence that the exponent on the factored form is exactly the multiplicity of that piece. We'll get into an example of how this affects the graph, but before I get that far, allow me to present to you the fundamental theorem of algebra. The fundamental theorem of algebra states that a polynomial of degree n has n real or complex roots counting multiplicity. So when you have a repeated root, you count every time it repeats. We deal with complex roots, which we'll address in a few moments. And you can double check that you found everything by verifying that if you have a degree n polynomial, you found n roots. All right, so let's take a look at another function. Let's look at g of x, which is going to be x plus 2 squared, x minus 1, 2x minus 5 cubed. The first thing I'm going to do is get all of my lead terms together as x squared times x times 2x cubed, which all told is 8 times x to the 6th power. Once again, we have a positive lead coefficient and an even degree. So we know that the end behavior is going to go upward to the right and mirror that by going upward to the left. Now, let's take a look at the intercepts. If I set 0 equals x plus 2 squared times x minus 1 times 2x minus 5 cubed, I get zeros of x equals -2 with multiplicity 2. I get a 0 of x equals +1 with multiplicity of 1. And I get a 0 of x equals 5/2 from that third factor. This one has a multiplicity of 3 because my exponent there is 3, right? So just grabbing the exponents and calling them the multiplicity. And if we add 2 plus 1 plus 3, we get 6, which is the degree of the polynomial. We can also look really quickly. G of 0 is 2 squared times -1 times -5 cubed, which is the absolutely huge number. Let's see, 5 cubed is 125, -125 times -1 is +125. Multiply that times 4 and you get 500. So we have a very large value on the y-axis. I'm not going to even try to get my scale right in the y direction. Instead, I want to really focus on what's happening here with multiplicity. So if I sketch out some coordinate axes, and I plot the points in question, x equals -2, x equals 1, x equals 5/2. I know that I'm going to be going upward, I'm going to be going upward, and I go through the point 500, which is way up in the stratosphere somewhere. Instead of simply passing through the axis, when you have zeros with multiplicity, the behavior changes. And the change in behavior is going to mirror the power functions. When you have x cubed, the curve does that weird jog over thing. Something like that. We call that a point of inflection. Again, those of you who are moving on to calculus eventually will study points of inflection in a lot more detail. Right? And then this thing turns back around and we go through the point x equals 1. That's linear, so it goes just straight through. And we come up to the top to that point and we curve back around. And then when we come down, this guy has multiplicity of 2. The graph of y equals x squared, the parabola, comes down on a point and then bounces back away. We call that sometimes a touch point, where the graph touches and bounces back off. So by using multiplicity, we can get a little bit more detail in what the curve of the polynomial is going to look like. We can start seeing some of the weird wiggles that are going to happen outside of just making sure it bounces and hits all the right points. With as convenient as it is to find the zeros of a polynomial when it's written in factored form, the obvious next question is, how do we factor a polynomial? And there is one simple trick, which is not quite as simple as it seems. I feel like I'm filming some clickbait here. But if you happen to know a zero of a polynomial, you can factor from there. So for example, consider the function f of x equals x cubed minus 8x squared plus 19x minus 12. There's no obvious starting point here, But if I happen to let you know, or you happen to find out somehow, that f of 3 is exactly 0, then we have something to work with. Because we know that f of 3 is equal to 0, we can split this thing up. We know that f of x has to factor to x minus 3 times something. What that something is, not exactly clear, but something. And so to find that something, we can divide. If we take x cubed minus 8x squared plus 19x minus 12, and we divide by x minus 3, whatever is left is the other factor. Remember the rules for polynomial long division. You mostly are going to focus on the lead term. X fits into x cubed. Well, x times x squared is x cubed, so I'll write down an x squared. And I'll multiply x squared times x minus 3, which gives me x cubed minus 3x squared. Now here's the trickiest part of the process. Just like long division of numbers, when you're doing long division on polynomials, you want to subtract. X cubed minus x cubed is 0. The lead coefficients always have to subtract off and become 0. If they don't, you've done something wrong. Go back and try again. Then we want to take negative 8x squared minus negative 3x squared. It's really easy to get confused and lose or add an extra negative sign. We need negative 8 minus negative 3, which is negative 8 plus 3, which is negative 5. So we have negative 5x squared as our new lead coefficient. I'm going to get rid of that 0 because it's just going to get in the way, and then drop down the next term, which is 19x. Right? Then the process repeats. I take x, goes into negative 5x squared. Well, you multiply x times negative 5x to get negative 5x squared. And if I multiply negative 5 times x, that's negative 5x squared. And negative 5x times minus 3 is plus 15x. And we subtract. Again, be careful, make sure you're subtracting. That's where most of the mistakes happen in polynomial long division. Negative 5x squared minus negative 5x squared is 0. 19x minus 15x is 4x. All right, that lead term has to be 0, but we're not going to write it down because it's just going to get in the way. And we'll just write down that we have a 4x here. And then we drop down the last term, which is minus 12. And once again, we look at the lead coefficients. X goes into 4x. Well, x times 4 is 4x, so I'll write down a plus 4 up here. And I'll multiply 4 times x minus 3, which gives me 4x minus 12. When I subtract that off, 4x minus 4x is 0. Right? Lead coefficients have to subtract off and give you 0, otherwise you made a mistake. Then we have negative 12 minus negative 12, which is again 0. Since I have nothing else to drop down, 0 is my remainder. If I ended up with a non-zero remainder, that would mean that this function did not divide evenly, and that what we had wasn't actually a zero of the polynomial in the first place. In this case, it did divide evenly, so this is a zero, and that tells me that I can factor f of x into x minus 3 times x squared minus 5x plus 4. There's a whole process of figuring out where the zeros of a polynomial are. It's called the rational roots test. I'm required to mention it, so there I've mentioned it, but I don't find that trying and repeatedly trying and looking for zeros is all that interesting. So instead of worrying about how to figure out where a zero is, let's worry about what to do with it once we have it. So we've somehow, through magic, been told that 3 is a zero of the function. We realize that means that the function has to factor to x minus 3 times something. We use long division to figure out what that something is. Now we have x squared minus 5x plus 4, which is a quadratic. And quadratics, we do know how to factor. This quadratic has a lead term of 1, which is easy mode. I need two numbers that multiply together to give me positive 4 and add together to give me negative 5. X minus 4 and x minus 1 works perfectly. And with that, we now know all three zeros of this particular polynomial. Let's take a look at one more function like this. Let's try g of x 2x cubed plus 7x squared plus 10x plus 6. And we've learned somehow that this particular function has an x-intercept at negative 3/2, 0. Right? Having an x-intercept at negative 3/2, 0 means that this is going to factor into x plus 3/2 times something. Now, one nifty trick that I can use here, I really don't want to deal with the fraction if I can avoid it. And I notice that I've got a lead coefficient of 2 in my original polynomial. So instead of x plus 3/2, I can multiply, let's do that in a different color. I can multiply this term times 2 and the other factor times 1/2. Doing so lets me write this in the term 2x plus 3 times something. Right? My something has an extra 1/2, which may or may not lead to a fraction, but my chances are better of not having a fraction because I haven't forced one there. So it makes my life a little bit easier. But regardless, we're going to set this up doing long division. We're going to take 2x plus 3, and we're going to divide that into 2x cubed plus 7x squared plus 10x plus 6. And so we pay attention to the lead coefficients. We have a 2x, we have a 2x cubed. If you multiply 2x times x squared, you get 2x cubed. And then multiplying the whole thing, 2x cubed plus 3x squared. Subtract. Again, subtract, make sure you're paying attention to sign, S-I-G-N, positive or negative. 2x cubed minus 2x cubed is 0. Lead coefficients go away. If they don't, it's a sign you did something wrong. 7x squared minus 3x squared is 4x squared. Drop down the next term, which is 10x. And the process repeats. We look at 2x, we look at 4x squared. 2x fits into 4x squared 2x times, because 2x times 2x is 4x squared. So I'll write the 2x up here, and I'll multiply. 2x times 2x is 4x squared. 2x times 3 is 6x. And if I subtract there, I get 4x. Drop down the last guy, which is plus 6. And one last time, I look at 2x, I look at 4x. 2x times 2 is 4x. So I'll write down a plus 2 up here, and I'll multiply. 2x times 2x plus 3 is 4x plus 6. I'll subtract that off. I'll get 0. There's nothing else to drop down. I have a remainder of 0, which means that this divided evenly, and that means that I can write out the factored form g of x is 2x plus 3 times x squared plus 2x plus 2. Now, x squared plus 2x plus 2 is a little bit tricky. It's quadratic. It's easy mode with a lead coefficient of 1. But there is no number, there's no pair of numbers that multiplies together to give you positive 2 and also adds together to give you positive 2. There are no two numbers that do that, at least not two integers. So we can think fractions, we can think complex numbers, we can think irrational numbers, hopefully. When all else fails, there's always the quadratic formula that's available, right, to find the roots of this polynomial. Either 2x plus 3 is equal to 0, which means that x is negative 3 halves. We already knew about that one. Or x squared plus 2x plus 2 is equal to 0, which means, busting out the quadratic formula, x is negative b, which is 2, plus or minus the square root of b, which is 2 squared, minus 4 times a, which is 1, times c, which is 2, all over 2 times a, which is 1. Two squared is 4, 4 times 2 is 8, 4 minus 8 is negative 4. And the square root of negative 4 is 2i. So we end up with a pair of complex roots. We have one real root and two complex roots, which come in a conjugate pair. Remember, a conjugate is complex numbers that have plus or minus. The plus form and the minus form a conjugate pair. That's literally what it means. And when you have complex roots in a polynomial, they always come in a conjugate pair like this. The real root is the only one that we will graph. The complex roots are going to cause the function to have some sort of weird behavior somewhere far away from the x-axis. What that behavior looks like is beyond the scope of this course. We're focusing on how we can interpret the changes to the x-axis, or near the x-axis, I guess I should say. This means that there's going to be something weird happening far away from the x-axis, but if we just graph what's happening at the x-axis, we'll get something kind of close enough. Up next, I want to change gears a little bit. And think about writing polynomials. If we know the polynomial in factored form, we can find all of the zeros. If we know all of the zeros and their multiplicities, can we write a polynomial? For example, if I want to write any polynomial function which has roots x equals -2, x equals -1, x equals 0, x equals 1, and x equals 2. Well, to get a root of x equals -2, the function must have factored to have x plus 2 times something. To get a root of x minus 1, the polynomial must have factored to x plus 1 times something. To get a root of 0, you must have had a factor of x minus 0, or just x. To get a root of positive 1, you must have had a factor of x minus 1. And to get a root of positive 2, you must have had a factor of x minus 2. By simply writing out all of the necessary factors, we force ourselves into a polynomial. Now, there's not a lot of detail given about this polynomial. We could take any of these roots and raise it to a power, because it doesn't say that the multiplicity of each of them is 1. We could multiply in some other stuff, because it doesn't say that these are the only roots. We'll fix that in the next problem. Another thing that we could do that's really not going to change anything at all is to multiply by something in front. Multiplying by something in front, you've seen previously, will scale vertically the graph of a function. We can use that to, after we start writing a function, make sure that the y-intercept is correct along with the x-intercepts. Right. So one more like this. Let's look at a function that has zeros at x equals -3, x equals +1, that one with multiplicity of 2, and x equals +7/2. Let's also say that we want this function to have a y-intercept of 0, 2. Right. Now we are a little bit more constrained. All right, now let's take it a step further. Not just any function, we want the polynomial with the smallest degree that exhibits this behavior. In order to do that, now we know that we want, well, we can put some coefficient to get an x minus 3. That means, I'm sorry, to get a 0 at x equals -3, that means we need a factor of x plus 3. To get a 0 at x equals 1, that means we need a factor of x minus 1. To get that to have a multiplicity of 2 means we have to square it. And to get a 0 at x equals 7/2, we need x minus 7/2. Although, to make my life a little bit easier, instead of calling this x minus 7/2, I'm simply going to multiply that thing by 2 and write it as 2x minus 7. Again, we have an arbitrary coefficient in front which just absorbed the 1/2. Right? Factor out a 1/2, put it into that a. We're going to figure out what a is in just a moment. But until we get there, at least we don't have fractions, which makes our lives a little bit easier. Because the other thing we need is the y-intercept 0, 2. Remember, the y-intercept is what happens when you plug in x equals 0. Well, f of 0 is a, times 3 times -1 squared times -7. Right? When we calculate all of that, 3 times 7 is 21, -1 squared is 1, 1 times -21 is just -21. We get -21a. And what we needed was 2. So simply dividing, we see that that coefficient needs to be 2 over 21. And that introduces our fraction f of x is -2 over 21 times x plus 3 times x minus 1 squared times 2x minus a thing that doesn't at all look like a 7. Right? And with that, we've now written the equation of a polynomial. It's exactly the process of graphing a polynomial, but completely backwards. Next, we turn our attention to rational functions. A rational function is any function which can be written as the quotient of two functions where each of those two functions are polynomials. And when you're dealing with rational functions, one of the things that you learned early on in previous mathematics courses is that rational functions must always be reduced to their lowest terms. There's a lot of weird corner cases that can come up if your polynomials happen to have a common factor. For those of you moving on to calculus, one of the big things you learn there is how to deal with that situation. For our purposes, we are going to simply assume that P of x and Q of x have no common factors. And when you have the situation of no common factors, then the places where the denominator is equal to 0 form what are called discontinuities of the function. And very specifically, each of these discontinuities takes the form of a vertical asymptote. An asymptote is an auxiliary line that we draw to help us better shape a graph. To show you what I mean, let's look at a very simple example. Consider the function f of x equals 1 over x minus 1. This has a discontinuity when x minus 1 is 0, which means that x is equal to 1. And that discontinuity is going to take the form of a vertical asymptote. So if I sketch in my coordinate axes, I'm going to draw a vertical line at x equals 1. I'm putting it in red and I'm putting it as a dotted line because it's not actually part of the graph. And what's going to end up happening is that the graph is going to head up towards that line over here and head down towards that line over here on the other side. The other thing that's going to happen on this graph, and frequently happens on the graph of a rational function, is that we're going to get a horizontal asymptote. If Q has a larger degree than P, right, the polynomial in the numerator has a smaller degree, the polynomial in the denominator has a larger degree, then there is a horizontal asymptote at y equals 0, which I did draw in this curve, although I didn't really mention it. Scrolling back up for a second, the other bit of behavior, if I go along y equals 0, the x-axis, as the graph trails off, the curve comes closer and closer to the asymptote there. And then the last thing, the function is going to have roots or zeros when the numerator, p of x, is equal to 0. There's a couple of weird things that can happen, but by and large, the behavior of the roots or zeros is just like a polynomial. So if I have f of x is x minus 1 squared over x times x plus 1 times x minus 3. Putting all of that together, I notice, first of all, that my zeros are going to be when x is equal to 1, and that has a multiplicity of 2. I'm going to have vertical asymptotes when the denominator is equal to 0. That's x equals 0, x equals negative 1, and x equals positive 3. The numerator has degree 2. The denominator has degree 3. Since the degree of the denominator is bigger than the degree of the numerator, there is a horizontal asymptote at y equals 0. So, sketching out some coordinate axes to work with, I can draw in my horizontal asymptote and my 3 vertical asymptotes. Along with my 1, 0. I don't have the benefit of end behavior that I had previously. So figuring out where this graph is going to be above the x-axis and where it's going to be below the x-axis is a little bit trickier. In order to do that, I'm going to look at these regions. The only way that the rational function can cross from one side of the x-axis to the other is either to pass through the axis or to do something at one of the asymptotes. So if I think about where the zeros and asymptotes happen to be, -1, 0, +1, and +3. I can pick a couple of points in between. And if I can figure out whether the graph is positive or negative, whether the function is positive or negative, that tells me if the graph is above or below the x-axis. Right. To the left of -1, something like -2. Well, my numerator is something squared. That's always positive. My denominator, the first term, if x is -2, that's negative, and that's negative. Negative times negative is negative. So over here, the function is going to take on a negative value. Between -1 and 0, something like -1/2. Again, because the numerator is squared, that's always positive. Well, this is still going to be negative, and that's still going to be negative. But if the value is bigger than -1, this is going to be positive. So we have negative, positive, negative, which is positive. To the right of 0, well, that hasn't changed anything. The numerator is still always positive. To the right of 0, this guy is now positive. This guy is positive. Something like 1/2, this is still negative. So we have a negative result here. Between +1 and +3, something like 2. Once again, this is always positive. When x is +2, that's positive and that's positive, but that's still negative. So I'm negative in this part. And finally, when x is something bigger than 3, like say 4, once again, this is always positive. When x is 4, that's positive and that's positive. And now this thing is finally positive as well. So we have this alternation, negative, positive, negative, negative, positive. And with that last detail, I will be able to draw this graph. Because over here to the left of -1, the graph is negative. It's heading towards the vertical asymptote. It's heading towards the horizontal asymptote. Between -1 and +1, the graph was positive. So it's going to head towards this asymptote, and it's also going to head towards that asymptote. There's no 0, so it doesn't touch the x-axis. It's just hanging out somewhere way up in space. Between 0 and 1, the graph was negative, which means it's going to head down towards this asymptote. Between 1 and 3, the graph was still negative, so it's going to head down towards that asymptote. And to the right of 3, it was positive. So we're going to head up towards the asymptote here and trail off that ways somewhere or another. And with that, we've drawn the graph of a fairly complicated rational function. Right. With that, I'm going to wrap up this discussion on polynomials and rationals. Thank you for joining me as always, and I'll see you next time.